Thanks. It's nice to be back to Sheffield again. And yeah, this is the talks will mostly aim at answering your questions. Many of you already heard 2 talks about the Gaussian process and probably know before attending a Gaussian process is computationally expensive. And you see all the nice properties and wondering, and does it ever going to be usable if it is computationally expensive, so expensive? And here I just try to give some idea about where is actually exactly computationally expensive and what kind of a trick in the general sense does the Gaussian process the research community has been exploring. So what are the things are quite useful. And I know this is the end of the last talk of today, so I try to stay light on the math, try to give more intuition. And so first what we are talking about is again this object Gaussian processes. You have been seeing in quite a few times, and just a little bit capital notations. The X is usually a bunch of the input, which is a bunch of vectors. I just write a capital N of them, and a Y. In this case, is a scalar Y. And this particular example, X is scalar as well. And F given X, P of F given X is a Gaussian process written as a multivariate normal distributions with 0 means, and the covariant matrix is specified the kernel function. And in these regression examples, we are assuming Gaussian noise distributions. Throughout these examples, we'll only talk about regression with Gaussian noise distributions. Tomorrow, there will be more lectures covering more complicated cases like a non-Gaussian Gaussian process with a non-Gaussian likelihood and other applications. Oh, come on. Go away. So Nicholas already talked about a little bit about fitting the Gaussian process. Here I just want to mention often when we talk about the computational expensiveness of a Gaussian process, what we are usually refers to are 2 possible steps, because given a Gaussian process, we usually do 2 things. One is to find the values of our hyperparameters that are usually involved in the parameters of our kernels and parameters we assume for our likelihood. And then often choices is doing maximum likelihood estimations. But of course, if you go with a sampling approaches, you will not go with a maximum likelihood estimation, but go through drawing samples about your hyperparameter. But that's a separate thing we wouldn't talk about here. And another things you would do with a Gaussian process is after finding a set of meaningful hyperparameters, you want to know the predictions of your model given the observed data, which we call predictions. For the particular case of Gaussian process with a Gaussian noise distributions, this prediction is a closed form distribution, which is exactly multivariate normal distributions with a particular structure of mean and covariant matrix. You will see such kind of pattern again and again. So the general pattern is basically come from the conditional multivariate normal distributions. So in both of these 2 type of tasks, one central component we would compute is the covariant matrix. Given capital N number of data point, we will compute a covariant matrix K, which is n by n. Each element or each entry of the covariant matrix is basically evaluated the covariant kernel functions over the pair of the data point. Here, just showing a very common choice of kernel, which is square exponential, and you can plug in here any other type of kernels. This is in general how the covariant matrix get computed, and it's quite easy to see. In particular, in these cases, the complexity is n squared q because we have n squared entries. Each of them take a complexity of q. And if we want to do the maximum likelihood estimate of the hyperparameters, what do we do? Like we briefly showed before, we will find the parameter maximize the log of the likelihood, which is this term. And when we spell out these distributions, it's basically we just spell out the multivariate normal distributions, which is basically the log of determinant of the covariant matrix and a quadratic form with y and the inverse of a covariant matrix. For people are not totally familiar with how it actually gets implemented, Nicholas already briefly mentioned, but let's just mention again, is that in practice, we're usually implement these covariant matrix inversions via Cholesky, which is the most numerical stable solution to solve this value numerically. And after we obtain a Cholesky decomposition of the covariant matrix, and the rest, the lower bound can be write down in terms of the log determinant is basically sum of the log of the diagonal of the triangular matrix, because it's a lower triangular matrix. So the determinant is basically summing the log of the diagonal entries. This term, the complexity is n. And the quadratic form becomes L squared norm of the L inverse y. This is n square complexity. It's quite easy to see. This is a constant. So the overall computational complexity of computed the log likelihood is n cubic, n plus n squared plus n. So it overall is n cubic. So that's how exactly the n cubic complexity comes from, where when we compute the log likelihood, we can run a very easy profiling over computing the log likelihood. You can see this is the percentage of the time taken for each line. This is a line for computing the kernel. This is a line for computing the Cholesky. The Cholesky is n cubic, which is not surprising. It takes quite a lot of time. And this is come on. In practice, you will also notice, this shows exactly in practice, you will often notice that the computation of the kernel also takes quite a lot. Covariant matrix take quite a lot of time, because it have to handle quite a lot of data, so where the queue may be quite big sometimes. And overall, this take quite some time. And this is just a complexity. This is n cubic. For people who are not so familiar with computational complexity, people may wonder, what does it really mean, right? Why cubic? We're so concerned about cubic. Why we talk about a linear or quadratic, we are much more calm, but we talk about a cubic or higher order polynomial, then we are quite nervous of complexity. Here, I try to give you a very simple numerical analysis, is that exactly for that previous examples, I did a small time profiling. I choose a few number of size of the data between 10, 100, 500, 1,000, 1,500, 2,000, and compute again the log likelihood. And this is the time it takes for each size of a data set. For the data set of 10, it takes 1.3 millisecond. Then the second is 8.5, then gradually going up. Even with 2,000 data, it only takes like less than a second. It all doesn't look take a lot of time, right? And then when we plot it on a graph, I then try to fit a curve. I use again here's a Gaussian process with a polynomial kernel. A bit matter, but then we can see both the mean and the error bar. We see it quite nicely. Cubic curves. And of course, there's some measurement of noise, because it's actually a computer CPU runtime. There's also other factors that influence the runtime. So it doesn't look too bad, right? The 2,000 data point only take less than a second. But now imagine if we have a 1 million data point, how long it would take. We can put extended graph of a Gaussian process prediction. and look at how long it will take at 1 million data, it will take actually roughly 3 years. By the way, it's wrong on my laptop. It's quite a lot, right? And
how does it compare with QR?
Oh, QR is also n-cubic. And QR are for square matrix, you usually would take Cholesky, not QR, because in that cases, Cholesky is a little bit more stable than QR usually. But for those linear equation solvings, you often can formulate it into QR as well. Cholesky is usually more stable, and speed, for the squared matrix, I don't think there's a major differences. But for a non-squared, those sparse linear systems, then there is performance differences. If you look into solving those low-rank linear equation systems, then you can solve either with Cholesky or QRs, and in that case, QRs usually is a little bit slower, but numerically more stable. But if you want, we can have a discuss offline. Yeah, it's only 1 million data point. It take on a very, very toy example, it take 2.3, roughly 3 years. And that is remember, that's only one step, right? We only evaluate the objective one time. So of course, we actually, if we really want to find the good hyperparameters, we need to run a gradient optimization. So it's not a single 3 years, but a 3 year multiply with a number of it's a gradient step you are going to take, which is will end to be not possible to wait. And then, of course, one counter argument would be, well, we know the computers has been become faster and faster quite rapidly, and in particular, nowadays we still can observe, if you following the hardware performance increases, like we can observe, for example, like a 20% single process runtime increase 20% year by year. So I try to show a simple math that if we wait about 20% year-over-year increase, and if we wait about 10 years, how long it would take? How long it would take for it to compute a GP log likelihood for 1 million data point? It turns out it would be takes about, for 10 years it takes about takes about 176 days, and after 50 years it will goes down to 3 hours. So it's not so quick, but you may feel it's not still may not be waitable, but we also have parallelism and other things. But one factor I want to also emphasize here is that the complexity goes cubic, and that means that whenever we double the size of the data, the amount of computation it has to handle goes 8 times more. So that means when we double our data size of the data, it will take another 12 years to catch up the speed if we only have a 20% year-over-year increasing of the hardware performance. So overall, in the end, I just want to deliver the messages that rely on hardware itself, and it's a little bit harder to wait for the hardware to naturally going fast enough so that we don't have to worry computationally, the computational speed. And also the other thing is GPU and the CPUs are quite popular nowadays. It gives a little bit of different angle because it's vastly parallel, especially GPUs. But one challenge about applying Gaussian process computations on GPU is that, or especially on multiple GPU or the multiple CPU machines, is that the computation, especially the Cholesky decomposition, is quite heavy in communications. So most of the current implementations are rely on shared memory, so which doesn't scale well, or mostly doesn't scale well with multiple machines. So the performance increase on the cross-machine parallelism is also not very promising. This is basically a small diagram about profiling about a few of the current parallel implementation, including GPU implementation over the Cholesky, which is the factors, the runtime goes with a size still goes quite high when the data size increases. So anyway, so the short message is to say like the hardware itself is probably quite hard to wait to automatically solving our problems. Then alternatively, the research field it has been doing is to find approximate algorithm so that although we cannot solve the exactly answers with a very fast speed, but if we find the right approximation algorithm, we may find approximate answers with good enough accuracies with much more small amount of time. And what I want to show in the rest of the talks is a few mostly 1 and 2 strategies people has been doing to speed up or approximate Gaussian process computations. First is that often, especially on the real data, a lot of data does not necessarily means the underlying relations between the input and the output data are necessarily very complicated. And especially on business data, on real data modelings, you will often observe is that the relation between data are relatively simple, and there's a lot of noise. That limited the amount of regulation you actually can capture. For example, here I use an example to show that although the function is a quite simple 1D functions, we can just have a lot of data to represent these 1D functions. With this huge amount of data, that of course makes the computational very expensive, but that does not actually means the underlying function is very complicated. So when we encounter such situations, the most straightforward reaction would be, what about just randomly subsampling our data, right? Because if our underlying function is quite simple and we have that means we have too much data, so why don't we just look at a small chunk of our data? And for real data, is often, unfortunately, the data are not evenly distributed in our input space. A naive data subsampling, in these small toy cases, what I try to create is there's more data in the centers, less data at the two sides. And then whenever we try to do a random subsampling, the area with less data will very likely to leave it out. So we will very easily miss out the data point at the locations where there's less data. Imagine if we miss out one data point at here, then the function curve goes up instead of predicted down. That would dramatically change the prediction of our functions. So these things can happen. Imagine you have more than one-dimensional functions. This kind of changes can happen at many locations. So that basically shows that why just blindly data subsampling wouldn't actually easily solve this problem. And if we closely look at this kind of examples, and what it shows here is to plot out the actual covariant matrix when we computed from the previous example. What we often notice is by having so much redundant data, what we immediately observe is there's a low rank structures in the covariant matrix. What on the left plot is the histogram of the covariant matrix on the left hand, and on the right hand is the value of the eigenvalues of the covariant matrix function sorted from the high to low. You can see beyond like a 10 is already going to be very close to 0. So one direction of approximate Gaussian process is to exploit those commonly low-rank structure in the covariant matrix. And in the literature, one of the first methods that have been proposed to doing such a things is called Nystrom approximations by Chris Williams and Matthias Ziegler. The idea is quite simple. If we have capital N number of data point denoted as X, let's just randomly subsampling our training data into a smaller subset called Z, which only containing a capital M of them. And then we can compute both the covariant matrix over the same kernel functions between Z and itself to be the KZZ, and the cross-covariant matrix between the original training set X and our subset denoted as a KZ. And then we can write we can approximate our original covariant matrix K by a covariant matrix K tilde, which is written as a KZ inverse and KZ transpose. This looks a little bit interesting structure, but one characteristic of this structure is that imagine Z is the full set of X. So if the Z equals to X, then the KZ will becomes K. Both KZ and KZZ will become K, and then one K and K inverse will cancel each other. Then the K tilde will become exact as the original K. So that means in these cases, with this kind of structure, if our subset is a full set, this is actually an exact representation. So it's only low-rank approximations if we are choose a subset of our data set. And the Nystrom approximation is basically plug this K tilde into our log likelihood, which becomes this form. And this is low rank because in the middle, this covariant matrix is only M by M. So this covariant matrix overall at most have the rank capital M. And one thing is if you directly write down or expand these log likelihood terms, you would not immediately gain any computational benefit if you do it naively, because overall this covariant matrix is still M by N. So one trick people play here is called a Woodbury formula. What it does is it basically rewriting this inversion into this form. The important here is that the middle inversion part is a M by M matrix instead of a M by N. So the calculation of this log likelihood then reduced to the complexity of an NM square, because you don't have to invert a covariant matrix of M by N anymore. And of course, we just previously discussed the limitation of randomly subsampling the data, and then immediately the first criticism of the Nystrom approximation would be, now you're doing the data random subsampling again. Isn't that actually not quite useful? That is actually one of the limitations of the Nystrom approximation, is the original algorithm actually does not come with a nice way to sampling subsampling the data set. So it's proposed as naively random subsampling, and later in the literature, people proposed the idea of using pseudo data. So the idea is that instead of subsampling the data set, let me just switch off the Wi-Fi, otherwise it's getting too annoying.
It really wants you to connect to your station.
Yes. Later, people then try to tackle the problem. People propose the idea of pseudo data, so that basically the idea is slightly different. Then instead of taking a subset of the true original data set, what about summarizing the information of the original data set into a small number of pseudo data, so that then we can use the pseudo data to represent our model, and therefore we can have more efficient computations. This line of ideas, and one of the first method is called FITC, which is known as a fully independent training criteria. The idea to do that is they first introducing the pseudo data as a small number of data which does not observed, but it is jointly modeled together as our original data. So our original data is X and Y. Now we are introducing some data we do not actually observe with output U together with Y, and its corresponding input location Z together with X. So expanding the training data with some data we didn't actually observe. And then similarly, we can expanding the Gaussian process into covariant matrix. The block covariant matrix can be written like this, which is KUU is a covariant matrix over the auxiliary data U, and the KFU is a cross covariant matrix between the pseudo data and the true data, and the KFF is a covariant matrix over the true data. And one property of a Gaussian process is that with the previous joint distribution, if we marginalize the pseudo data U out, we will result into the exactly same distribution as before, as a distribution over our training data alone. This kind of a property means that we augment the data without changing the prior distribution of our model. That's actually quite important. And secondly, we rearrange the joint distributions into a conditional distribution, so that we first we rewrite it into the prior distribution of U and the conditional distribution of P of Y given U. And similarly, we can just written these two distributions in this form. One is multivariate distribution. The second is a conditional multivariate distribution. So with the previous slide, we introduced an auxiliary data, but we see it directly fall back or equivalent to the original model. So it does not introduce any artifact, but of course it also does not introduce any benefit. So to make it computationally efficient, in the FITC method, what they do is that the original form of this covariant matrix is not a low rank at all. The original distribution of P of Y given U is not a full rank covariant matrix. It's because the KFF component. This is low rank, this is diagonal, this is a full rank. To make it computationally efficient, what they do is they make these two components diagonal. So they basically took a diagonal covariant matrix from this covariant matrix. So they element-wise multiply with an identity matrix and a plus with a noise. So this forms the approximate model of FITC. With these approximations, the covariant matrix becomes a diagonal covariant matrix. With these forms, then we can marginalize out the U, because the U itself is also a multivariate normal distribution. So following the standard trick, we can marginalize the U, which gives us these distributions, this covariant matrix in the marginal distribution. So the marginal distribution looks like these things plus a diagonal matrix plus another diagonal matrix. These things can be computed efficiently from the Woodbury equation again. Just like the equation we showed before, you slightly augmented the way we treated the equations, basically put this and the sigma I together, and then we result into a similar Woodbury equations. The middle component is again the m by m matrix. Therefore, the FITC approximations is the complexity of nm square. So this is the first pseudo point approximations. The bigger benefit and this approximation brain is then the pseudo point do not has to be on top of training data anymore. That allows us to optimize the location of the pseudo data. In fact, you will actually run gradient optimization to find the best location of your pseudo data. Then can avoid the problem or come with the random data subsampling. So that if you allows way to optimize the location of the pseudo data, then the gradient optimization will move the pseudo data to cover the whole training data as much as possible. But it also come. And also, the other thing about FITC is it also combined quite nicely with another approximation algorithm called expectation propagations, which can allow you to easily deal with non-Gaussian likelihood. And there's also a connection with version of Sparse Gaussian process. I wouldn't go into details, but just to mention, FITC has been quite successfully applied and also with EP as well. Yep. Go ahead.
We're talking about strategies to reduce computational effort.
Yes.
And now you said, okay, this is one approach to do this, but also we might have to actually optimize the location of our pseudo data again. Can you comment on like how that relates in terms of computational effort that we also like, introduced by having such a procedure? Like, is that how does that compare to something that we say?
Good point. That's a good point. That's actually over omitted when we talk about computational complexity. One thing, so I can give you try to explain one observation is that if you have a not so big of a data set, you can observe is a standard Gaussian process can converge with gradient optimization with a few iterations. If you run with a BFGS, you usually can converge with like tens of iterations. But if you run with a pseudo or sparse Gaussian process approximations, the gradient optimizations will usually take much longer. You can depend on different type of approximation you choose, but you usually easily can go into the magnitude of 100 iterations into the 1,000 of iterations. So that's for sure. At each gradient step, the computational cost, the complexity of computational cost goes much lower. And the price you pay, you probably will take more steps to converge because now you not only have to optimize the value for your kernel parameters, you also have to optimize the location of your pseudo point. Having said that, but the problem is the cubic complexity goes very quickly. And also the other effect I didn't explain here, but also Nicholas explained a little bit is the standard Gaussian process or plain Gaussian process also have a quadratic memory consumption. So both computation and memory, you will often quickly get stuck when you have roughly more than 5,000. If you go with GPU, you can go usually up until like 12 to 13,000 data point. Then will be usually the limit you can run with a normal even cloud computer. And the sparse Gaussian process would allow you to go into much bigger without a memory issues usually, and you can converge with a much bigger data set. You can easily go with tens, hundreds of thousands of data points, even like millions of data points. They are usually fine. So that at the big end, when you have really a lot of data, then you gain back the computation efficiency, although you still have to optimize your inducing point. But if you only have like a few hundred or even like 1,000 or 2,000 data point, plain Gaussian process will be a better choice actually.
So you mentioned that the locations Z at the pseudo data could be optimized via gradient optimization, but what objective function? I don't understand what is the objective function.
And the objective function is basically your log likelihood.
The one that contains all the original data
Yeah. Yeah, for example, this one will be the one for the nitrogen, basically the log likelihood over your training data. That is usually the objective.
Expanded data.
Yeah, yeah.
So just a small question, isn't optimizing the locations of several different input points at once very prone to, like, isn't that very difficult to optimize if you have to place multiple points at the same time?
It actually surprisingly not, because it doesn't have to one match to each others, right? It basically kind of try to have a cloud of a point to explain another cloud of point, right? And then you can imagine the objective sense that there's quite a lot of some area of data point is not getting explained. It will try to push the data point that goes there. So it's a more close to there where the pool will be more stronger, so that it's kind of moving the overall, all the inducing point that goes into there. So it kind of not too bad, I have to say. You can try yourself. The gradient optimization is usually will give you quite a nice explanation of the overall data set.
So I guess for that question, I imagine for a Gaussian likelihood, that's convex, disjointly convex in all of the pseudo data locations. But you mentioned that also this trick works pretty nicely to some connection to sparse variation of Gaussian processes for non-Gaussian likelihoods. But I guess I wonder what are the guarantees of the optimization of the locations when the negative of likelihood may no longer be convex.
Yeah, and also for complicated models, it's also not necessarily convex. But usually, you will also not initialize your data or inducing point all into a single locations. You will actually try to, a common practice, we will just, like, for example, randomly choosing subsampling the training data as initial locations of your pseudo data. So that will initially already randomly, quite randomly spread across the input domains. And then the optimization is usually a little bit of fine tuning where need how much inducing point to explain the function or something like that. So this usually can result into quite good solutions, but it could be tricky in some practical examples, especially tricky things go together with when you jointly optimizing the inducing location and the kernel parameters. And then the inducing location will influence what is a good kernel parameters, because if you, for example, inducing point all very far away, then the kernel parameter cannot be, or for example, length scale cannot be very small, because it doesn't make sense to explaining a very wiggly function, because it does not have enough inducing point to explain support that function. So these two things can interplay, then the optimization get more complicated. But in practice, it usually works quite well. Any other question? No? Okay. Let's go. Let's move on. I mentioned the FITSI, and I have been saying, yes, we are able to optimize the inducing point location, but there's actually one problem about the FITSI, about optimizing inducing point with location, is that it actually changed the model. If you see the definition of FITSI is we actually explicitly approximated our model assumption or our conditional distribution in the model definitions from the true ones into diagonal one. This conditional y given u. This, of course, is not correct, and then that will cause many complicated effects. There's actually quite a few machine learning papers explaining this effect, and one example people often given is that optimizing an inducing point of FITSI may lead to overfitting. And there's a separate approaches which is following a slightly different philosophy, but have a related math. Is an approach called sparse Gaussian process or variational sparse Gaussian process. That approach is, what it does is instead of directly changing the model definitions, it tries to embed the sparse approximation into a variational posterior. So in that sense, under that framework, no matter how you move around or how you represent your pseudo data, it will always be a lower bound of your original marginal likelihood. So that in that sense, the gradient optimizations will always make it better. It will not overfit. So the technical details, what it does is that it again assuming a set of pseudo data U and Z. U is the output, Z is the input. And following these conditional distribution formulations, exactly similar equations, what it does, instead of changing the P of F given U, it defines a variational lower bound, which is inside assume a variational posterior Q of F comma U. In the variational sparse Gaussian processes, it assumes a particular form of variational posterior, which looks like this. It assuming a parametric posterior of QU, which is the posterior distribution of our pseudo data, and directly taking our prior distribution P of F given U together to form the posterior distribution of Q of F comma U. And if we directly plug these terms into our variational lower bound, the instance benefit you can see is these two, the numerator and denominator cancels out, which result into a quite elegant variational lower bound. I will not go into details about how these things get derived. And one thing I want to highlight is the complexity of this overall resulting lower bound becomes again nm squared, and we also can find the optimal Q of U values with closed form, and when we plug in the optimal value of Q of U into the original bound we derive here, we result into a tighter bound, which is usually being optimized. And if we look closely at this lower bound, it looks very similar to the Nystrom approximations, apart from one extra term here. It's a trace term here. And this overall computational complexity is nm squared. And yeah, I skipped quite a lot of details, but the main difference between the variational sparse approximation and the FITSI is instead of we changing the model, here we define a variational posterior. One, for example, benefit of this is that because it's a variational posterior, we can give whatever number of inducing point. We can give like the number of inducing point way more than the number of the data we have. That will not result into any overfittings. It will still give us a good explanation of our data, so that you can freely optimize the inducing input locations without worrying about the effect like overfittings or side effect on the kernel hyperparameters. Make sense? Cool. And the second part of the talk, I will just very briefly go through another line of approximation people do is previously we'll talk about the things we call a sparse Gaussian process, which is rely on the assumption that what if our data are kind of quite similar to each other, so that the covariant matrix are low rank, so that we can nicely approximate our whole training data with a subset of them, so that we can do quite a computation efficient calculations. For all the problems, the covariant matrix are necessarily low rank. Here I will want to give counter examples. That of course for many problems, the covariant matrix are totally not a low rank. This particular example is basically, for example, if we have a time series where t is a time and y is some value we observe, we try to model a relation between the time and the output value. And the time we can just continually sampling at a fixed interval. For example, let's start with a sample at the zeros, and if we sample at 10 data point until the t equals to 1, we get for example, this kind of a data point. And if we fit a Gaussian process, this will be the mean and the covariant matrix, or the uncertainties the function looks like. And on the right-hand side will be the covariant matrix. It looks like a diagonal heavy one. And let's then continue sampling 100 data point. And this function looks like this one. So we will basically come from here, sampling this data point. So we get 100 data point. The covariant matrix looks like this. And if we're sampling 1,000 data point, this overall function, for example, if it looks like this, and then the covariant functions will look like this. So you can see the covariant matrix is gradually approaching to a diagonal covariant matrix with more and more data, because we are sampling more and more into the futures, and the data point at a nearby 10 point are always correlated to each other. So of course there's no low rank structure exists, right? So just give you this example is just this kind of examples will not work well with sparse approximations, because it's very hard to assign or approximate the data with a small set of data, because when the time goes on, it will be always correlated, and it's never going to be a low rank structure. But in this very particular style of problems, there's actually a nice solution, which is in these particular examples, this data point, the example I'm giving, the data is actually sample from a Markov chain or Markov process, where every data point is actually only depends on the previous time point. And it is known that for such kind of processes, or for such kind of Markov processes, we can derive a covariant matrix or a kernel functions, which is known as a Matern family, where the covariant matrix function is not a low rank, but it's a precision functions, it's a banded precision functions. So that allows us to do a quite efficient calculations by directly computing the banded precision matrix and directly solving the either the log likelihood or the prediction. So in these cases, then this style of approximations, which is actually related to a field of research, is called stochastic differential equation, which has a Gaussian process interpretations, which is exactly following this family of approaches, would be quite a nice solutions to solve this kind of problem. And this just to give you a brief ideas, like if we have a closed form precision matrix, then we can directly calculate a lower triangular of the Cholesky decomposition of the precision matrix, then it can compute it in these forms where the overall computations will only be linear to the number of data point. So this is quite nice examples when you don't have a low rank approximations in your matrix, but this particular method is of course also constrained to the examples or the situations where you have such a kind of a Markov chain dependency. And also one other thing, limitation you can easily see is that it works quite nicely for one dimension, which will give you a banded covariant matrix. But if you have a two-dimensional structure, then it will not be a banded precision matrix. It will very likely have a, like those off-band saying, it will become much more complicated. Anyway, also just mentioning, just mention this. I showed two style of approximations, and the main idea behind them is that different approximations are usually need to fit into the right type of problems. you have to choose the right type of approximations that fitted for your problems. And there's also many more different type of approximations that people are developing. For example, their approach is to do a stochastic frequency approximation or deterministic frequency approximation by using the frequency decomposition of a covariant matrix and approximating the covariant matrix calculations by using a subset of the frequency. And you of course can distribute it. There's approach to distribute your data set and do a local computation of Gaussian process instead of building a single bigger Gaussian process, which is known as the distributed Gaussian process. There's also other lines of approximation Gaussian processes using conjugated gradient. This is a family of a method to use a conjugate gradient method for solving linear equations systems being used for solving Gaussian process calculations, which also works quite well. So our examples are the method, for example, called the KISS-GP, or nowadays they have a library called a GPyTorch. These are kind of lines of method that use the conjugate gradient. Just mention there's many also other different type of approximations exist. That's all for the talks. Thanks. Questions?
So I think Michael Stein published a paper in 2014 where he talked about low-rank approximations to Gaussian processes being limited to applications in at least spatial statistics. If I remember correctly, I think most of what he was talking about is that they tend to interpolate like too smooth a surface for the applications that he cared about. Is it your sense or intuition or experience that this insight like applies elsewhere, or is it sort of a limited to spatial statistics fallback?
To some extent, yes, because one way I usually view those low-rank approximation, or in a particular example like a variational sparse Gaussian process, is that the number of inducing points actually gives the upper limit of the complexity of your function you can have, right? For example, in some kernels, one inducing point will give you one wiggly of the functions. Then, for example, you have 100 inducing points. Then for that 1D function, you will maximally be able to have like 100 wigglies, right? Of course, that limits the complexity of your functions. And then, if your underlying data are really complicated, and then the maximally the functions can do with low rank or those inducing point approximations, it will give you the maximum complexities the function can give you, try to match the data. Then it often, of course, looks smooth. And then there's another effect is, of course, in the variational sparse Gaussian processes, you will, if you optimize the kernel parameters, it will also find the kernel parameters to give those smooth functions so that it can work together well with limited number of inducing points. So it will work together, gives you relatively smoother functions than the actual data have. If your data are more complicated than the model can explain, but that is totally true. And if that situation happened, then the alternative question would be whether there exists another approximations that can give you complicated enough functions. For example, in the time series cases, in that particular examples, if you use stochastic differential equation method, then that can give you quite a complicated, nice fit. But that, of course, exploit that specific structure of that problems. And that does not, of course, apply to general problems. And then in general, those low-rank approximations in general works quite well without much assumptions of your data, of your problems. But if you have a problems where there's certain properties you can explore, then there will definitely better approximation to dedicate it into exploit those properties for sure. Make sense? Oh.
You just had a short comment on that, because another way to see it is like, you can think about it as like you're fitting a parametric model to a non-parametric model. That's one hand-wavy way I've always thought about these things. And because I think you should think about it in terms of model mismatch, because it is a non-parametric model, you can pick the wrong prior, which is an RDF kernel. It's wrong for everything, right? It's infinitely differentiable. Give me any data that comes from a physical system that's infinitely differentiable. You can't, right? And now you can flop that with data, and basically your prior will be less important. Now you're saying, oh, actually, I'm going to have a smaller number of parameters. Now your prior becomes more important. And it's your prior assumption that becomes more visible, if you want. So I don't think it's the approximation per se, but it's a model mismatch. Because the way you can think about it, if you're choosing 100 inducing points in this case, you're still fitting a model with 100 degrees of freedom. I don't think there's any problem that has more than 100 degrees of freedom. It's just that you're fitting the wrong parameters, because basically your model is wrong, but it's not that visible if you have, you know, an RDF kernel. If you got data everywhere, it's fine, right? So I think that's another way of thinking about the problem. So, yeah.
Yeah.
So for example, in time series example, I guess in a practical sense, you could say that the points that are far apart really don't influence each other anymore. So are there standard solutions, for example, to combine local GPs that all only look at points that are close to a certain point of interest, and then slide local GPs over your input space and combine them?
If it is not for example, the particular case of the SDEs, if you try to build a general GPs, try to do exactly what you say, and the challenge is that in the covariant matrix, those data points are not influencing each other, but it can influence others through some other data point. You know, because everything is correlated. The GP actually has two data points are correlated with some other data point, and also even the data are very far away, they are influencing each other through the same kernel hyperparameters. So although there are many works on the distributed Gaussian process to try to exactly do this, to say like if we look at locals, we probably don't have to worry so much about global. They work quite well for many practical cases, but often it's very hard to directly build a nice theory framework so that they become approximation of a single Gaussian process, because this is quite hard to manage in those different correlations and inferences. So what you described is true, but it's hard to become a clean approximations. More questions?
So for the distributed approximation, is there any way to weight kind of the local estimates according to, say, their marginal likelihood on the full data or on the larger data? Because if you have equal weight given to GPs that say received a very unrepresentative subsample of your data, I wouldn't want that GP to be as, taking up equal weight to, say, an estimate that was given a very representative subsample of the data.
Yeah, I do not totally get it. You're basically asking it is difficult to weighting different local GPs, or
yeah, that's right.
And actually the even bigger challenge is if at the intersection of two GPs, how you can combine the uncertainty together. Combining the mean together is usually, you can find many ways, like weighted sum or whatever, but it is very hard to find a nice way to combining the distribution together, because you also want a nice connected uncertainty together. So overall, it's actually a quite hard thing. So I think the distributed GP, a few papers, they try to come up a nice way to actually exactly try to produce nice uncertainties, but still you can see that that uncertainty is still significantly different from as if they're actually under a single GP. So I think there's still gap there to be done, things to be done. More questions? And that's all. Thanks.